Okay, we are going to go ahead and do computational problem number 2 now from test number 4. I hope you guys appreciate how much when I look at these tests, look at these questions, they're like, oh, what's that? It seems like it was so long ago, I forget all about these things. All right. At the North Pole, the Earth's magnetic field is 7 times 10 to the minus fifth Tesla. Assume the field is created by a current loop circulating 2,000 kilometers from the center of the Earth in the plane of the equator. Assume the radius of the Earth is 6,000 kilometers. How large is the current? Looking down from the North Pole, in what direction is the current moving? Oh, yeah, I might have to give you a pass on the what direction the current is moving, because I didn't explicitly say that that was a plus, that it was in the positive direction. I'll think about that. I'll see what the answers look like. Okay, yeah, that's what I want to do. All right, so what do we have? We have the Earth. We have the Earth. Let's see. And once again, oops, I forgot I was going to check on this. I'm going to go ahead and draw this X, Y, and Z. So what do we have? We have in this XY plane here, we have a current loop with a certain radius. I'm just going to call that RC for the R center. Meanwhile, we are at the North Pole, which is straight up there, a distance of the Earth's radius away. I'm just going to call that distance D. And so let's go ahead and make this a simpler looking problem. And the simpler looking problem is just this. It is, we have X, Y, Z. We have a current loop here, and we're at some point here. So we know that we have some current that's moving in some direction I. We can always flip this around the other way if need be. Some direction I. So how are we going to calculate the current up here? Well, we're going to use Biot-Savart law. Biot-Savart law is just mu 0 over 4 pi I dl cross r over r cubed is equal to the d sub b. Some little increment of magnetic field is just created by something. Okay, so we are going to, this is our dl. Okay, I'm going to calculate this the same way that the book does. There are a couple, we could do this component by component, but we can also do it the kind of easier way, which is we're just going to look up here and say, all right, here is at some point here. Oops, I drew that too far because this is just supposed to be this distance. This distance, d here, what is that distance equal to? Well, it's equal to, oh no, shoot, I already used d, because d is this distance. So, and I already used, let's see, what did I call this? R sub c. R sub c. All right, so let's call this, I'll call it big D because I'm lazy. Okay. All right. So what is big D? D is simply square root of d squared plus r sub c squared. Okay, so now let's look at this, what the result is here at this, for this location right here. We have I dl, which is in this direction. We have r, which is in this direction. So we are going to cross r, and what are we going to end up with? We're going to end up with a dB that is like this. Well, let's now go ahead and look at another spot over here. What if we were looking at this spot over here? What would we have? Well, we'd have the exact same geometry, except now our dB is going to go in this direction. So from this and from the symmetry of the problem, you can see that the component of B which is in the plane, which is normal to z, is going to disappear. Therefore, the only thing we need to be concerned about is the b sub z. Well, what is b sub z? So db sub z, the little bit from right here, is just, let's see, how do I want to define this? Let's define it like this. We'll call this angle alpha, which means this angle here is also alpha just by, oh, that was interesting. Just by geometry. Euclid can tell us that this is, because we know this is a right angle. And there, yeah, okay, so that's it. So we know this angle here is equal to alpha. So what do we have? This dB sub z is just equal to dB. I write it this way. dB sub z is equal to dB, the overall magnitude, times cosine alpha. Oh, no. I think I got that wrong. It's op over height. Yeah, so it's sine alpha. If I am now correct. Let's see. So if this goes to 0, then b sub z goes to 0. So yes, sine alpha. Okay. Oh, so now what is alpha? Well, what's this angle alpha here when we look at this alpha and this triangle here? This triangle here. I'm going to pull that triangle out this way. This is the triangle. It's r sub c is here, and it is, what do we call it? Little d there. Yeah, let's do it like that. I'll leave it at that for the moment. So this alpha here is just okay. I'm going to do this. I'm just going to go ahead and write in d squared plus r sub c squared, which we already figured out. That's this d right here. The reason I'm going to do that is because I don't really want alpha. What do I want? I want sine alpha. And if I do this, I can get sine alpha. It's just r sub c over this. So this is equal to dB r sub c over square root of d squared plus r sub c squared. Okay, so that's d sub b sub z, and now all I need to do is take this integral. Well, what is dB? Well, we got that up here. Oh man, okay, so dl cross r is, we already figured that's dl sine theta, but we know sine theta is equal to 1, so that's just dl r, which is big D right now, and r cubed is just this, once again, this r is this distance from the dl to the point where we're trying to get the magnetic field, so that's also d. Making this a little crowded. I'm going to rewrite this. Matter of fact, let me back up. I'll just rewrite it more neatly over here. Mu 0 over 4 pi. None of that changes. I does not change. The dl cross r is just dl d sine theta, which is equal to 1. So that's just dl d, and oh, and I'm sorry, and then our r cubed, which is just d cubed. So what is that? We're going to cross that out. We're going to have d squared down there. So this is our dB, which we now have a magnitude, the magnitude dB, and then we're going to do this to give us the z component of that. So what do we have? We have d b sub z equals mu 0 over 4 pi I, yeah, dl, where are we? dl sub c, I'm now pulling that from up here. And then this, what is this? This is just d, but we already have a d squared here, so let's go ahead and put that all together because that's going to be d squared plus r sub c squared. Okay. Did I miss anything? Mu 0 I over 4 pi dl over d squared. Oh, excuse me, I did miss something. That's not. Over d squared. D squared is just d squared plus r sub c squared. But we have one more of those. So we really have this to the 3 halves. Okay. Or I could have just written this as big D cubed, but big D is equal to this, so this is D to this to the 3 halves. Okay, so what's DL? Well, a more convenient way to talk about this DL would be as R sub C D theta, where this angle here is theta. So I now can rewrite this DL as r sub c d theta, but I'm just going to make the r sub c right there, and d theta. And so what do we end up with? I am now going to erase all this stuff. Okay. Yep, I can erase that. Okay. So now we have b sub z is going to equal the integral of mu 0 I over 4 pi r sub c squared over d squared plus r sub c squared to the 3 halves d theta. Well, what in here depends on theta? Nothing, except for d theta. So I can take this and just put it right here. And then what are the limits of this? Well, we're just going all the way around the circle, 0 to 2 pi. So we just replace this with a 2 pi. But we see we have 4 pi right there. So what do we have? This is just take this and divide it by 2. And we now get rid of, I'm sorry, not divide it by 2. Cancel out a 2. Well, I guess, yeah. Okay, and there's our answer, B sub z. What are we asked? Oh, how large is the current? So how large is the current? So once again, we're going to do what we did before. We're just going to rearrange this for current. So what do we have? We have B sub z, 2 times B sub z, d squared plus r sub c squared to the 3 halves over mu 0 r sub c squared. And this one I did, I used actually real numbers from the Earth, and so I didn't do anything to make this one come out to a not so unnice number. So I am just going to fill this in as saying it's 2, what's b? 7 times 10 to the minus. Yeah, I can't remember what this comes out to be. Then, let's see, what do we have? D is 6 times 10 to the third. Squared, plus 2 times 10 to the third, squared, to the 3 halves, and that is over 4 pi times 10 to the minus 7th, times 2 times 10 to the third. Oh, wait. Yeah, sorry, I'm going to fix those in just a second. 10 to the third squared. Okay, however, I wrote this in kilometers and we need it in meters. So this is actually 10 to the 6th, 10 to the 6th, 10 to the 6th, and everything else is the way it should be. Okay, so I'm going to stop this video here because I do not want to do all these squares and cube roots or cubes and square roots by hand. So I will put this in a calculator and come up with a number. But that's the answer right there. All right, here's the big amazing result. After putting all these numbers in, and I'm just doing this for completeness, I get 2.2 times 10 to the 10th amps. Okay, it's a lot of current, but the Earth is pretty big.